Well, a couple of videos ago, I introduced the concept of source and load impedances, and we were really talking about, I was talking about, in that those videos matched impedances. And of course, a device has an output impedance or a source impedance, and this is its ability to pass current out from it elsewhere. And the load impedance, of course, is it's also known as an input impedance, is the device's ability to pass current through it. And it's really all about this ratio or the relative source versus load impedance that all these lectures are about. We talked initially a couple videos ago about matching impedance and how important it was in high frequency devices and long distance devices, and this includes telephone, video, digital audio, data, and antenna lines, to really have these impedances matched between them. And here's a nice chart here that kind of shows the common impedances. This should have been in the earlier video, but it wasn't. Wireless microphones like we use at NESCOM, 50 ohm to 50 ohm. Word clock, MADI AES, SBDIF, analog video, SDI. Those are all 75 to 75 ohm. Cat5 is 100 ohm. AES3, which is AES EBU on an XLR cable, that's 110 ohm. Analog phone lines, 600 ohms, as well as early analog audio. Early analog audio was also 600 ohms. So we got to talk about telephones for a moment, because the audio started in telephone. In fact, a lot of what we use today, phone plugs and a lot of things, they all come from the analog phone world. And in those days, the phone company, the Alexander Graham Bell company, the Bell system, they determined the most efficient way to do this, to set up their systems, was to match impedances, because they were going to be long distances and they were worried about return loss and they didn't want echoes. And it's possible some of you guys have heard echoes on an analog phone line before I have, and that's really an impedance issue. So obviously when you call your grandma in San Francisco, the phone line is much longer than the wavelength of the signal, so it's really important that you have matched impedances. And so the phone systems were matched. Another important thing, and the reason why they matched back in the day, was that matched impedances guarantee the most efficient power transfer. And that's kind of a complicated statement to unravel. A better way to say it is they guarantee the most efficient power transfer in a tube circuit paradigm. Like really in the world of tubes, having matched impedances as a source of load in the era of tubes was the most efficient way to transfer power. And when you're sending a phone conversation down 60, 100, 300 mile long, I mean, obviously I don't think they're going that far. You're going to have amplifiers every once in a while, but you're trying to get as much power as possible. Amplifiers are expensive, metal is expensive, tubes are expensive. As far spaced they can put those amplifiers, substations, and relay systems from here to San Francisco, the better. So maximum power transfer was important. Now, the audio industry pulled all of its early technology from the phone industry. The phone industry was the initial audio thing. And everything was vacuum tubes. The vacuum tube comes on the market around 1904, I think it is. I think that was when Lee DeForest invented it. And so tubes are certainly at the heart. We didn't start seeing really, amplifiers and that sort of thing in audio until the mid-1920s. And all this stuff is tube. And so the audio industry now, like the famous gear that we all think is legendary now, really comes from the 1950s. I'm talking Pultecs and LA2As and that kind of stuff. A lot of that gear is tube-based, as you know, and tubes have a really high source impedance. The output, take that back. A very high output impedance. Tubes have really high thousands of ohm output impedance. And this is an issue for a variety of reasons, and which I will discuss later in the lecture. And so what the solution was to take a transformer and hang a transformer on the output of your tube. And the transformer would step down the voltage, and along with it steps down the impedance. Because impedance steps down with voltage, it just does it by the square of it. So if you've got a 10 to 1 transformer where the voltage is going down by 10, the impedance is going to go down by 10 times 10, so by 100. So anyway, all that nerdery aside, the transformers were always connected with tubes. And this is heavy and expensive and can be problematic. So all early gear, and there's a Fairchild up there, probably the most legendary compressor of all time. We're talking $35,000, $40,000 if you can find one. And of course, there's a Pultec, so very famous 1960s EQ, and everybody wants these things. And they're all built to be 600 ohm output and 600 ohm input. They followed the telephone company system. And this is cool, and it works fine until there are any, anomalies, any real issues with matching the output of your Pultec and plugging it into your Fairchild. You start getting changes in level, and you start seeing potential distortion and potential frequency response issues. And the other issue is it's very hard to split your output. You can take a Pultec and you can split it to 2 channels, so to take its output and put it to 2 channels on a console, but you're actually going to lose half your voltage. You're going to see the signal level drop by 6 dB. And that's not something you really want to do, because you want to keep your voltage as high as possible so it can be as far away from the noise floor as possible. So impedance matching had some issues. And all of this changed when the transistor was invented. And the transistor, replaces the tube for the large part, unless you're, an audio purist. And the transistor comes out, I think, about 1947 or so. And it's really not until the 1960s that the transistor becomes the norm in electronic circuits, especially in the audio industry. And so what you're looking at right there is an op amp. That's an operational amplifier. An operational amplifier is an integrated circuit. Well, that one's not an integrated circuit. That's a discrete circuit. But it's a circuit that amplifies. And there are zillions of these things. I mean, literally zillions. There's hundreds of these things in the API Vision at school. And they're in the 1608. And oftentimes when a channel doesn't work in the 1608, you open the thing up and you pop out the op amp and you put a new one in. And that's what an op amp is. Well, those guys right there, 1, 2, 3, 4, 5, and these things as well, are transistors. And those are definitely transistors. And those guys are some sort of integrated circuit potentially, or is that just a heat sink? It's hard for me to know. But there's a lot of transistors in an op amp. And what's cool about op amps, what's cool about transistors, is they offer almost 0 ohm output impedance. Very, very low output impedance. And this is a stark transition from tubes that offered a very high output impedance, which means you don't need a giant transformer on the output of this thing. You could put one on there if you want, but you don't need it. And so this totally changed the paradigm of the electronics world and the audio world, because now we could use this tiny little thing. This particular thing's about 1 inch by 1 inch, and you can even get micro versions of this that are, way smaller than your fingernail. And these things, they work as amplifiers, and they're more efficient, they use less power, and you can have really low output impedance, which lets us get to a whole new model of impedance, which is called impedance bridging, as opposed to impedance matching. So I'm about to stop the video. I just want to say this is really important. I've talked about impedance matching so far. I'm now talking about something completely different called impedance bridging.